with Scott Yin as our cloaking speaker today. So Scott Yin graduated from UIUC, so he's a PhD, and then he worked at Microsoft Research in Seattle, Redmond for a while, 10, 15 years?
12.
12 years. Yeah. And then he moved to an Institute of AI Research, the other side of the lake in Seattle. And then now move back to the other side of the lake, back to Facebook AI Research.
Still in Seattle side, actually. Yeah.
So he's now at Facebook AI Research, which is part of Meta. And Scott Yin's research career really is a reflection of the progress of the community, which kind of like the search, QA, knowledge-intensive task, where he has multiple very famous work at different part of the growth of the community, for example, including semantic parsing, knowledge parsing QA, which was one of the famous people winning the February Award 2 years ago. And in the early days of word embedding, he also has done a bunch of very interesting work, including the exponential understanding of word embedding. And after that, he has done a lot of work in OpenQA and with benchmarks, algorithms. And later on, with BirdRBC, Scott Yin was one of the leading contributor and innovator for dense retrieval RAG. Actually, RAG is your paper.
Yeah.
And then after that, he was working on a large language model pre-training, especially in the multimodality side, with like Camera was one of the early work that early fusion for multimodality with image and text token pre-training from scratch. And now in this talk, he will share us with his new adventure about factual and physical generation with retrieval. So let's all welcome Tony.
Thank you, Tony. Okay, I know there's no microphone, so I'll try to speak louder, but let me know if you guys cannot hear me clearly. Yeah, so I use factual and faithful generation with retrieval as the title, but really it's kind of like a sample of some of our recent paper on factuality space. Yeah, so let me start from some introduction of that. So these days, when you have some kind of question or you want to learn something about that, for example, tariff is like hot keyword these days, you may actually have this question. In the old time, you probably just actually use Google, Bing, or this kind of search engines to get some information. But because of the popularity of large language models, and it's getting more common that you just ask ChatGPT or Meta AI or any other kind of large language model. And those models actually give you quite like nice summary of the topic and then kind of highlight important things that you may want to know. In fact, it's actually based on some survey, people are increasingly switching to the likes of ChatGPT, this kind of large language model. Say 27% of these respondents in the US use AI tools instead of search engines. And reasons given include efficiency, ease of use, accuracy, and personalization. Okay. So this is probably not just a personal experience, and then this is a trend that's happening. However, the question is that, is it really trustworthy, right? So you get some information from large language models responses, and then are they really correct? So as my coworker, Akari, she probably gave a similar talk here, and I used her slides over here. So at some point, she was wondering that whether there are some interesting papers already published on the topics that she cared about. And then so she asked GPT at the time. And not surprisingly, GPT actually gave a very confident answer, and then it's so smooth and very, very relevant to her question at the time. But if we check closely on the papers like listed by this response, actually nothing exists. And then so it's really concerning that, okay, even though the information presented seems to be so well-formed and seems to be true, and actually there's a lot of like false information over here. Okay. So let's take a step back and look at how large language model or language model is done. So the simplest form of that is really like it's really generating the next word, next token based on the sequences of the things that it has already generated. And the training process is really just like to maximize the probability of the right token that you observe, we observe in the training corpus. The main feature here is that the training corpus nowadays is actually very large. For example, I think Llama 3 used 10 trillion tokens to train the model. And in this case, for example, here we see that the capital city of Ontario is Toronto. And then in this case, because the model has seen a lot of these kind of occurrences in the training corpus, and we hope the model to actually learn these things. Some people call it so-called parametric memory of these kind of facts observed in the training corpus. And during inference time, there's no access to the original training corpus. Instead, we just actually want the model to automatically generate those kind of things. And in this case, we hope that the model actually really predict Toronto is the right next token and right answer for this continuation and with the highest probability compared to other alternatives. However, this actually works pretty well for the general head kind of entity, other things. But if you try something more like a tail knowledge, then I think in this case, Akari tried to use her name as the starting point and then ask, what's the next token after this sequence? And then the model cannot really predict that, okay, either she was a student or she was a researcher or so on. And then, so in this case, we know that at least for tail entities and the large language model's predictions or responses could be wrong. And people have found that this kind of issue can be mitigated quite well using retrieval. And more specifically, we use retrieval to actually get relevant information during inference time. The information is relevant to the original input. So the very high level way that it actually works is that we assume that we have some kind of data store. It could be just a large collection of documents. It could be a structured database. Basically, we just have some data over there. And then we have built an index so that we can actually access the relevant information quickly through the index. And once we have the input to the language model, we also form some kind of query, usually just through some part of input as a query to search the index and then find the relevant piece of information. And then together with the original input and the model output, and then we generate the final output of the whole system. Okay. And that's basically another way to say that is that there's some information we actually incorporate from some information from the data, so we incorporate at the inference time. Okay. So somehow RAG has been a thing, which is something we didn't foresee when we wrote the original RAG paper. And really, when people talk about RAG these days, it's really a simple augmentation of the retrieval things. And usually it consists of two steps. One is that when you have some input, you use that input to help you to find k relevant documents, k chunks or whatever. And once you have that, then you essentially just like either prepend or append to your original input, the prompt, and then extend the prompt instead of input as the new input to the language model. And usually the language model actually does pretty well by generating the response condition on the augmented context input. So it's a mix of its own parametric memory and also the retrieved context in this case. So I would say that RAG actually substantially alleviates the hallucination problem here. So the hallucination problem, I mean, is that basically the model just fabricates the facts, and then you can really not find the support to actually justify that kind of generation. It's very effective in handling tail knowledge, and it's also very efficient in incorporating new knowledge. What I mean by that is that models are actually trained using existing corpus, and then so if there's a news event happening, then there's no way that it's the training data actually contains that. So using retrieval to actually actually give you a very efficient way to kind of bring in the new information without retrain the model from scratch. So with this, I mean, if you try today's language model, usually they kind of by default, they kind of incorporate their search component in their system. So I tried the same prompt myself. And this time, the response is actually quite good. So all 3 papers here are real papers. And the last one is actually the paper led by Akari. And then in addition to that, they usually put the link to the paper. So you can consider this kind of link as a kind of citation. So really justify that they really exist. It's not hallucinated by the large language model. So the question we ask is that, okay, remember that I used the word alleviate. So the problem still is there. It's not completely solved. So the question for us is, what are the things we can do beyond the simple RAG solution? Okay. The first direction is that, how about let's just make the language model itself better without the dependency of some kind of external knowledge, or at inference time, basically, can we actually improve the language model itself to give more factual responses even without retrieval? Okay. So the reason why it's appealing is that whenever you have additional component, additional dependency in your system, the system becomes more complicated. And so if there's a way we can remove this retrieval component, no matter how good it is, if we can remove that, basically you'll make the system easier to maintain and then also potentially more efficient. So that's the motivation of this route. It could be like maybe there's something we can do during the pre-training time, such as we can invent new memory architectures for better memorization. And this is one of our recent projects. So we basically design a spatial memory layer and then use that to replace some of the attention layers in the networks. And then we show that with more parameters, and then you actually memorize some basic facts actually better than the standard transformer multilayer architecture. Another is that through post-training, maybe not everyone actually has the resource actually to retrain the foundation models. So more practical solution is really just to get any kind of pre-trained model and then try to make it better. And this is also the so-called alignment thing. And then we have some method trying to make the model more factual through these kind of alignment methods. Okay. And the other direction is that there is definitely still some use case that retrieval is necessary. For example, there's I mentioned earlier, when there is new information, then we want to incorporate that. And also, you can actually broaden the notion of retrieval, not just actually relevant context. Maybe there's some kind of other online signal you can incorporate it. Okay. And then for that, the first things that we want to do is that we want to make the language model grant their responses in the augmented context better. So what I mean by that is that remember that model itself can already learn a lot of knowledge from the pre-training corpus. Okay, so even if we actually provide additional context, sometimes there could be some kind of knowledge conflict. By that I mean the language model actually remembers something. Its belief is actually different from what's provided in the context. So for that, one paper we had is this context-aware decoding thing. Essentially, this is based on the observation idea. So for example, when you have the original query X, and without any kind of augmented context, the language model may say that, okay, Argentina actually won 2 World Cups in this case. But if you provide context, then obviously now the correct answer should be 3 instead of 2. But because of the prior knowledge is so strong, so the language model actually still say that the answer should be 2 instead of 3, even given this context. Although if you actually look at the probability distribution, the probability of next token to be 3 actually is much better than previously when you are just trying to answer this question without the additional context. So in this paper, we basically designed a trick so that you compare these 2 scenarios and then notice that actually one of the tokens probability actually changed quite dramatically. So we should actually consider that and then make the language model really trust the evidence actually provided in the context. Another related thing in this case is really we want to provide citations. So given the additional context, whenever we generate some statement, we want to link it back to which sentence in the context that support this generation, this generated statements. Okay, so that's another thing we just did recently. And another angle for actually kind of use the retrieval component better in the inference time is that we can actually do more sophisticated things, such as iterative online retrieval and fact-checking. So if you are familiar with this domain, this is kind of related to self-RAG, but we kind of extend it in like 2 different aspects. One is that in addition to retrieval, we also can incorporate other signals like online fact-checking. And the other thing is that when we incorporate that information, we don't incorporate that as additional input that is still textual tokens. We actually can do it in the embedding space. OK, so I kind of just gave an overview on that. So I won't be able to talk every paper I mentioned. So in today's talk, my plan is actually first talk about the newest paper actually published last year, Flame. But in order to do that, I think it's nice to give a quick introduction overview on how factuality really is evaluated automatically nowadays. It's still an open problem, but I will probably use one of our paper, FactScore, as the starting point, and then use that to give some background, and then talk about the work of Flame. And next, I will pick the paper self-cite, which I think is kind of interesting and provide a very clean and simple method for people to use so that they can actually train their model to provide sentence level fine-grained citations. OK, FactScore. So this paper was published 2 years ago. I think this one was, if not the first, but one of the first papers like trying to do some kind of automatic model-based evaluation on factuality. The majority work was done by Siwon and Kalpesh, and then all the senior co-authors on this paper basically just actually provide some feedback and then advice or ideas. OK, so again, let's use one example. So say that you have an input prompt like this. You want to know more about this person, Bridget Moynihan. OK, and then you ask a language model. It gives you some output like this. It's actually very nice, right? So it's relevant to the input. All the sentences here are kind of about what this person's job and what's the significant things that she has done before and so on. And if you read it, then it's actually pretty fluent and it's coherent. Okay, and that's probably the scary part of large language model, that it says those kind of things so well. But how do we know that everything they say is true? So one question is that are they factually correct? And then so that's kind of dive into it a little bit. So the first one, this is true. She's an American actress and model, but she's not a producer. She is not in Grey's Anatomy, but in a different, I don't know whether it's TV or movies. And she did started acting, but at a different place. Okay, so as you can see that this is actually kind of mixed of true information and false information. So the first challenge is that, as I said, it's a mixture of true and false information. Okay, so some of the previous work basically just actually look at the whole thing as a whole, and to see if that everything here is true, or only that we consider this is true. So if you actually use this very strict way to evaluate a piece of generation, then the score you will get is just 0. But this is not really reflecting what we see. So there's still some value or something mentioned that here that are true. Okay. The second thing is that if we really want to actually kind of evaluate every piece of information manually, it's actually pretty costly, right? So you have to first separate them into some claims and then have human and maybe do some search to justify that whether it's right or wrong. Nevertheless, let's start from defining, what we mean by the factuality score here. So here is really a precision-centric method. So basically, what we did here is given this piece of text, we first decompose it into some facts, what we call atomic facts. So these are kind of simple things, very short. And then, for example, the first 4 atomic facts here is actually from the first sentence over there. Okay, then let's say that we have some knowledge source that we trust. In this case, let's assume Wikipedia is a trustworthy source. Then effectively, we just actually check the correctness of each atomic fact or atomic claim here. And then in this case, we have 2/3 of the facts correct, and then we say that the precision score here is 66.7%. Sorry. Okay. So what I just say is actually a manual process, so there's no modeling involved. And then here now is that, okay, if we want to make it more feasible, then we should, make model to do the work we just did. And so the basic idea is that with each of these kind of sentence, we first kind of break into claim and then use retrieval to find the relevant piece of documents or articles in the, say, in this case, Wikipedia or any other like trustworthy knowledge source. And then we use a model, maybe a language model, maybe some other methods, use a model to judge like, okay, given this article as the context, and is this a claim correct or not, okay, or supported by the retrieved article document. Okay, and then we try different methods to do this kind of, use it as a judge, and then we always start from a very simple baseline to make sure that everything goes well. So, for example, the done thing is that you can always say true or always say false, and then those gives you very high error. We try 2 different language models, on this slide, and then we found that if you don't have retrieval component, then you have a different bias, and then the error rate is still pretty high. So this is compared to like if you use a human annotator to actually give you the fact score, compared to using this system, using this model to give you fact score. But if you actually use retrieval, and then the error rate is much lower. So this actually becomes basically the final things that will decompose the claim and then have these atomic facts, and then use a search engine to find the relevant documents as a support, then use a language model to basically verify that whether each claim is supported by the retrieved context or not. Okay, so since FactScore has been around for 2 years, and then after that there are at least a couple similar methods. For example, this one is from Google, and they published in News last year. So basically, all the methods follow roughly similar design. So you have some response, we'll try to decompose it, and then try to verify each claim one by one. So the main differences here, I think there are 2 here. One is that instead of using Wikipedia, they basically trust Google search. So basically, they trust that, okay, whatever Google picked probably is the right knowledge source. And the second one is the in the original fact score, it doesn't really consider recall. It's just actually precision. So here they introduce recall, but it's really it's not really a real recall. So what does recall mean here? Recall means that there are certain time effects I really want the response to include, but it's hard to define. There's really, like given a prompt, like what's the Eiffel Tower, and then how many claims or how many facts we actually include in response. This is, there's really no true answer. So in this case, in order to have some kind of recall and for a number, so they basically said, okay, let's use this as the number of true positive there. Let's use it, let's make a parameter for that. So essentially, the number of true positive and then is basically kind of arbitrary and as a parameter. And the next one is the VERT score. Is also like it also appeared last year, and we think it is a better one because it also improves on top of SAFE. The main thing here is that it extracts only the verifiable claims. What I mean is that the original models, then there are some claims that actually not really the factual things. Sometimes it's a little bit subjective things that you really cannot find the right source to support, and it also is not necessary. And then the second improvement here is that they also provide a fine-tuned large language model for the claim verification part. So this is really primarily for saving costs. So you don't have to code the API to actually pay money every time you have to actually do some kind of fact-checking, verification type of things. Okay, so that was the kind of the background on the evaluation. So the reason why I mentioned that is that this is kind of like foundation. We need some kind of automated generated signals for us to actually to guide other methods to improve the factuality work. Okay, so next I'm going to talk about this factuality-aware alignment methods we published in NeurIPS also last year. Okay. So the motivation here is that can we make a large language model output more factual just through alignment in the post-training stage. So in this case, we're showing that we already have the language model, and we don't want to use retrieval or any kind of other dependency at the inference time. We just want to make it better. And then in this notion, in this current large language model like pipeline, this actually is kind of categorized in some kind of post-training phase, like people use supervised fine-tuning, reinforcement methods to actually kind of using preferential pairs to actually make the model better, and so on. And in this case, when we say alignment, basically we cover two methods. One is really just SFT supervised fine-tuning. So in this case, it's kind of upper part. We have some prompt or some question, and then we have some desired answer, and then we just actually use those as additional data to further train the large language model. The second part, the bottom part, is more like preferential things. So for the same input, same prompt, we may have different kind of responses, and then we prefer one response rather than the other. Then these kind of things can help us to create the preferential data to train the model, and then this in the reinforcement learning setting. So the original idea for this project was actually pretty straightforward. We were thinking that, we know that RAG, retrieval augmentation, actually helps a lot in alleviating this whole hallucination problem. So maybe we can do some kind of distillation. So we have a RAG model, and it's more factual than the model without the retrieval component. And let's just create some data and then use the standard methods, do SFT, DPO type things to make the model better. So because of the fact score was already there, and then so we use the data and then fact score as the things for us to do some kind of initial pilot study on that. Okay. So for this case, we just actually kind of find 500 different human entities to create the training data, and then the evaluation data is still the same provided in the fact score paper. Okay. So as I mentioned, that initial idea is actually just kind of like distill these things from the RAG model. So we first start, at that time it's actually a Llama 2 model, use the pre-trained model and with and without retraining, with and without retrieval. So this is like 1 and 2 here. The first one is just actually take the off-the-shelf language model and just try to answer, try to generate a response of those prompts about the bios of those human entities, and then check the FACS scores. And then the other one is actually hook up with some retrieval component to actually get relevant information, I think, from Wikipedia, and then have the model to generate the response. And in this case, as I mentioned that, with RAG, it does have higher FACS score, which indicates that it has more claims actually to be correct. So this is good. This is basically confirming our experience. Now, the interesting part here is that, okay, if we use the RAG model to generate data to do, and use that data to do supervised fine-tuning, so effectively that's kind of like distillation, we not only that we didn't actually improve FACS score, we actually kind of make it lower. So this is kind of compare 3 and 4 here. So we got lower FACS scores. And then how about DPO, the preferential data thing? If we actually we actually tried 2 different settings. One is that we just use the OJO model without retrieval, and then just sample some kind of responses, and then use FACS score to see like which response actually has higher FACS score, and then use that to create positive and negative pairs. It does actually help factuality a little bit. For example, compare 41.6 to 39.1. And then another method we did was like, okay, let's use the response from a RAG model, and then treat that as positive compared to the response from the OJO model, treat that as a negative. And by doing that, again, it actually makes the factuality score, FACS score actually lower in this case. Okay. So this is, we didn't actually expect this. It is a bit counterintuitive. So basically, when we do SFT, the labeled responses representing new information to the large language model. So what I mean by that is that sometimes the retrieval augmented version, it actually get new information from some maybe new news article or new corpus. Somehow the OJO model doesn't really have that kind of piece of information. Maybe this is the reason it actually promote hallucination. And then for the RO methods, and we also observe that standard reward often prefer longer and more detailed responses, but that also kind of give the language model more chance to actually hallucinate some and to make some false claims. Okay, and then at about the same time, and then other people from other organizations also have report similar findings. So this is actually from Google, and then published around the same time that they basically found that fine-tuning large language models using new knowledge actually actually encourage hallucination. Okay, so this is actually not just our finding, but also reported in other papers as well. So because of this pilot study, and then because of this observation, then we propose a kind of data generation recipe for us actually to do like better alignment work. So the hypothesis is that human-created instruction tuning data may encourage large language model to output unknown information or basically hallucination. And the solution is that maybe in this case, let's not introduce like new information. Let's just try to use the large language model themselves to generate responses, but do some kind of selection so that we know that there's no new large involved. So the process is kind of like this. Say that we have input prompt. And the first thing we do is that we check our database to see if there are existing tuning data that have similar prompts. When I say similar, it's not about like the same thing, like the coffee here, but probably like the same type of questions. Like in this case, maybe a generate like the history about Turkey or the history about other things. They are kind of in similar type of problem, similar type of questions. And then in this case, we can select some of the pairs here then to form the K-shard examples. And then we use these kind of in-context learning methods to and then fit into the original language model so that we have some responses for the original prompt here. And basically, these are the basis of our new SFT data. And for DPO, we first start from the model, fine-tune on the factuality-aware SFT data that I mentioned earlier, and create a new model. And then given an instruction, we use the new model to generate multiple responses, Y0, Y1, Y2, and so on. And then we use we basically measure like how factual these responses are, essentially using something very similar to fact score to score them. And once we have the score, then we can construct the preference pair, like for the same input, what are the good responses and what are the bad in terms of like whether they are factual or not. Okay. And in the end, we also want to bring in some other alignment data, because factuality is only just one dimension of the quality of the responses. So here we basically just do a very simple classification on whether this problem is about factuality or not, and it's kind of everything else. So if it's about factuality, then we'll include the method I just include the data I just mentioned, created by the method I just mentioned. And if not, then we just actually bring in the original human-created alignment data here. Okay. So overall, here is kind of the simple plot to show that how effective our method is. So on this plot, there are two axes. On the y-axis is basically factuality, using fact score as the way to evaluate that. But remember that factuality is just one dimension, and then we also want the responses to be fluent, to be coherent, to be relevant to others. So in general, here we just actually use a notion of helpfulness. Here is that we use apartheid eval to kind of compare the target model with the standard SFT plus DPO model, and basically do an A/B test on this one using apartheid eval as the way to evaluate the helpfulness of the response. I think the interesting conclusion here is I can see that the red Y is basically on our methods. Then so if you just actually look at SFT, then it's actually better than the original SFT methods on factuality and maintain similar helpfulness. And we see that adding the DPO data with this with our synthetic methods, then we don't have a huge drop in terms of factuality, but the helpfulness actually got improved in this case. So overall, it's kind of have some kind of balance between improving factuality but not hurting other dimensions. Okay, so that's basically that alignment paper. I think I will finish that, and then maybe we'll just save all the questions at the end. Okay, so let me go to the next part, self-cite. So as I mentioned earlier, this paper is really about like generating sentence level citation, and then so that the response actually can link back to the context. Okay, so previously I talked about like how to make the responses of large language models more factual, but there's always a question, right? So no matter how good the system is, as long as you know it's not perfect, you will always wonder that can we trust the response or not? And there's always a need that, even if we're pretty sure that this is right, we want to see the source and want to see like the justification of that. And this is generally provided by certain citation. But if the citation is just give you a URL link to a document, nobody's going to read that. So the more effective way is probably like, I can imagine a UI design that you have a cursor, and then when your cursor hovers on that piece of statement, then it kind of pop out the simple explanation, and maybe the one-sentence justification why that's correct. So in this case, we basically just like, okay, in this case, we already assume that we have some context, probably through retrieval that already given by previous system component. And then with this context and with this query, the model generates some responses. And then we want to know if some response is about some kind of factual statement, we want to know which sentence in the context actually support that. Okay. So before us, there are some methods already, but basically they are all, how should I say that, pretty standard. So they say that, okay, that's follow the standard paradigm. That's just use some way, either human annotated data or some kind of mixture of automatic generated data and human annotated data to create a corpus for doing this kind of supervised fine-tuning. For example, in this Longside paper, essentially what they do is that they first generate a lot of like questions and answer pairs, and then for each answer, they try to find chunk level citation using retrieval to see if it's relevant, and then refine it to be sentence level citation. And finally, have some model to do some kind of data filtering to make sure that have a good set of number of examples that have enough sentence level citation. And so they have this kind of sophisticated data curation pipeline to do that. So there's another paper which is kind of doing something similar, except that they were using the traditional NLI model, the entailment model, to tell that whether to do basically fact-checking type of things, and then use that to design a real model and so on. Okay. And such model can help them to create data for SFT and also use it for reinforcement learning. Okay. So the research question here is we asked is that can we actually, maybe create some data or some other methods to help large language model to cite without external supervision. Okay, and then so that's why we call the method self-cite. It's really like we build on the self-supervised rewarding mechanism via the method called context ablation. Okay. So let me talk about a little bit about context ablation. I think this intuition is actually very straightforward. So again, the input of here is that we have a question, and then we have a prefetched context that is supposed to be relevant to the question. And then given that, a model will generate the response R over here. Okay. Say that if the context doesn't contain the cited sentence, what will happen? Okay. So in this case, we can say that, okay, if this sentence is the cited one, this actually is the one that has heavy influence on the generated statement. If we actually remove that from the context, then we should expect that we'll have a very different response compared to the original one. The flip side is that if we only keep that cited sentence but remove everything else, okay, what do we expect? In this case, we'll expect that, okay, we probably will still generate the similar statements because the core information is there. Okay, so basically that's kind of the intuition here. And then more formally, how do we capture that intuition? And then in this case, we just actually measure the log probability of generating the response. For example, here we have the probability of generating the original response given the context, the full context in the query, and then what's the probability of generating this statement. Okay. Now, if we remove that cited important sentence, which is E here, if we remove that, then maybe the probability will drop. So that basically means that in this case, it's much less likely to generate the original statement. Okay. And similarly, if we just keep that and remove everything else, so the probability should be similar, the same, or even higher a little bit, because you can consider other things as noise in this case. Okay. Okay. So, in other words, you can consider the first case, which is actually removing that piece, how much probability drops by doing that. Because that piece of information, that cited sentence, is the necessary things that we really want to include that in the context. So that's why we call it necessity score. And then the other one is the sufficient score. So maybe that sentence itself, we don't need all of them, but having that alone is enough for us to actually generate that statement. Okay, so that's why we call it sufficiency score. And then we use the kind of the difference between this, the probability of the original generation, and also do this kind of ablation experiment as a scoring function. Okay, so this is just actually repeat what I said. So for the probability drop, it's really like the original probability minus the probability that the generation when you remove that key sentence. And probability hold is that you just have that sentence but remove everything else and then compare it to the original probability. Then the reward is basically the sum of these two, and through simple math, it's really just the final equation over here. So now we have a reward function. So how do we use that reward function? The first method is that we just actually use it at the inference time. So suppose you have already have a model like you do sometimes supervised fine-tuning, so you can generate the citation with this take like cite and slash cite, and then with the sentence number in between. And for this, we can just actually try different sentences other than 3, 4, 5 in this case, and then use this reward function kind of to judge, okay, let's try n different other combination and then see which one is better. If we try and find that some other sentences are actually having higher reward in this case, then we just actually replace the original prediction with EI here, which is the sentences actually that has the highest reward. Okay. We can also use that method, the reward function, actually to create data for us to do fine-tuning. In this case, is that we took the context document and query from the previous data set, and then we do this base event sampling, then create the preferential pairs, and then do the use the traditional method to do alignment using this pairwise data. Okay, so let's look at some experimental result. First is that we start from the long-side AB model. So this is from previous work. They already used the supervised fine-tuning data to actually kind of tune Llama model on that. So the model actually can generate the cite/cite, and then with some sentence number inside. But we use base of n to sampling to actually kind of replace those cited sentences, and also try the alignment methods. So each of them, and then we follow their setting. We try the methods on, like in this case, 5 different data sets to see, to judge the correctness of the citation. Here, the pushing recall one is all about like the correctness of the sentence level citation. In general, we found that both methods actually improve about 4 points compared to the original model. And these two methods are actually complementary, so you can actually add them together, and then it will improve like roughly 5.3 points compared to the base model. Another experiment we did is that because that starting model, it actually has some data curation, so it's not completely unsupervised. So we can also use another paper, which is unsupervised method, to create some pseudo label for us to do fine-tuning and then start from that model. So the starting point of that model is lower, not too surprising. But I think the general conclusion still maintains that with our methods on top of that, we can still improve like 2 to 4 points on citation F1, and in combination, we'll improve like almost 6 points on citation F1. As we were wrapping up this paper, and then Entropic basically provide an API that does exactly the same thing that we wanted to do, although they didn't actually mention much like exactly what what's the techniques they use behind. So, and also the model size, all that things is missing, so we don't know. But it's curious. I mean, we're curious to know like how our method compare to their API offering. So. So we compare our methods with some other proprietary models or through this API. And the first current part is actually, okay, just actually take the original API without much difference. And then in that case, we basically do better than all of them. Compared to the API from Entropic I just mentioned, we are behind, but only by roughly 2 points in this case. And then our model is a relatively small model. 8 billion model. So I don't know if we really can beat them, given that we don't know other model information, but it seems that it's pretty possible if our model is bigger or, or with some other improvement, we can probably do better than their offering. Okay. So I think this is the last one of last slide of this self-side work. So let me wrap up my talk today. This is more a mix of summary and also open questions. So I kind of mentioned 2 directions. One is that let's try to improve factuality without using any retrieval or other external information as the external dependency. Okay, and the first question is that can we actually do that by changing pre-training? This is still largely unknown. I mean, I had some discussion with some students earlier, and potentially it could be done through data selection or sampling or through some new model architectures. But we haven't, I mean, first of all, it's actually pretty hard to do a more systematic study in the pre-training space. And then we have done some model architectural work, but there's still more to explore. The fundamental challenge is that we don't know yet hallucination or this kind of non-factual generation thing is really inherent, natural, or by this kind of large language model design. So maybe this is broken fundamentally, and then we have to fix that to really enable the factuality problem. And the second thing is how about the post-training thing? Post-training is more practical, and we have done this framework, frame alignment method I just talked about. But there could be other new alignment recipes, or even some other crazy idea, for example, model editing. Maybe there's possibility that we can just do post hoc model parameter change to actually make it more factual. Another kind of like more popular trend these days is that we probably can use more inference time compute to do more reasoning. Maybe the model actually knows what's true or what's not, and we just actually need to encourage you to think more about that. So these are some of the things that we are currently exploring right now. Okay. The other direction is, okay, let's still try to use retrieval external information. The question here is generally like knowledge grounding and tracing. You can treat self-cite as one way to kind of do the grounding because it basically finds the things to cite in the context. Another interesting question a lot of people ask is that can we trace the source of knowledge in the pre-trained corpus? So if the model says something, can we pinpoint to a certain place in the corpus that this is the why and how you actually got this wrong? And then with that, maybe you can target it to do some kind of model on learning to actually kind of unroll this kind of behavior. Another direction is actually better interacting with the environment. This is actually also tricky because we also hope that the model knows its knowledge boundary. Basically, if it knows what it knows, if it doesn't know, or it could help it not to say something that it actually is not confident. And also, when you use the external resources such as retrieval, you can actually express the information need more accurately, either through the traditional discrete token like keyword query, or even just actually create query embedding in this kind of latent space. How to incorporate the external information better is also an ongoing and open problem. Right now, the way we use retrieval is kind of like having the model to use the tools that were actually designed for human users. For example, we use search engine by saying, okay, we type in keywords and some kind of understandable natural language query, and so that we actually expect model to leverage the existing tool using the same interface. But probably there are better ways to do that to actually enable the model to communicate with the external components. Yeah, so I think with that, this is my final slide. I can stop here and then maybe take some questions. Yeah, thanks everyone. Okay.
So when you look at this score, so a lot of it was like 53.
53. Okay.
Yeah. So how much context did you provide, and how confident are you that there's not a lot of redundant information in that context? So would that explain, for example, some of the observations that you saw that I removed this information, but that was not really important, but it actually was still there.
Right, right. So if I remember correctly, the context is more like a small chunk of like one paragraph type of things. It's actually not super long. But the candidate section, even though I mentioned about like sentence, but if you see the citation thing, sometimes it actually cites multiple sentences. So I think in the sampling things, I have to check the paper to see how the intern did, but in that case, we probably can, the combination probably you can select more than one sentence in that case. And so what you say is correct, right? So for example, maybe two different sentences, maybe not even close together, are providing the same information. So in this case, our method will probably break because we highlight one, but the important information is still there. But nevertheless, I think this captures the intuition that I personally think is actually very natural. Yeah. Yes?
Follow up, like if you were doing this for a very long document, let's say a book document,
right.
You would have to, like, would the solution be to, like, ablate every single sentence in the book document?
Yeah.
Which is 1,000%.
Right. So I should say that this is probably not designed for that scenario. So more practically speaking, if I have to design a system for that scenario, I probably would do like two-stage things. The first is really trying to find like, it's kind of hierarchical, right? So you first find the right chunk and then do things for there. And the whole context ablation method is really like sample something, try different combination to see if you can find that kind of signal here. So I would say that even in the scenario you mentioned, I don't think it's worth to do it at inference time. So because that just actually incur too much cost. But it's still possible to use like, to create training data and then try to use that data to make model better. So it's kind of like a line.
Yeah, about that, like, if you were to create training data, what would you have the model like output? Like, would you have it read out the sentence, or would you have like, in a sense, like, what would the citation model's action space be?
Yeah. So okay. So the training data part is really the kind of the second way we use to do. So in that case, is that we use the first methods and then still sample some sentences and then judge the score, and then we can kind of have this kind of responding, like the for each response, and then you have some kind of sentence level citation associated with that, and you use that to create kind of preferential data to do that model training. Yeah, I forgot I want to respond to other things. But anyway, I'll stop here. Yeah. Oh yeah, so another thing that I want to mention is that I say sentence, but this is arbitrary. So effectively, the same idea can apply to bigger unit. So for example, if you say that instead of using sentence, I want to use a chunk as a basic unit, and the same method actually can be applied.
Yeah, because like the sort of like action space of the citation model depends on what you're referring
Right.
to. And
Right.
if you were to do it in training time, the model would essentially have to learn to count or
Yeah.
point
Yeah.
in
Yeah.
its context.
Yeah. So really, I think the core thing is really just this nice observation and this design of reward without like using additional supervision, just by like observing the model's performance, you can already get pretty useful inside information to guide you to improve the model. Was there other question over here? Or? Yeah.
Do you think hallucination is resolved in the sense that it's as good as a typical search engine? Or does it mean resolved?
You mean that even though we know that there's still a lot of false information in the internet, but usually the top 10 from Google, Bing are pretty reliable?
Hopefully, yes.
Yeah.
As people don't complain as much about.
I feel even with simple retrieval augmentation, it's actually happening. Like, even though I'm doing factuality related things, and then one problem I encounter is that to make slides, I have to find some bad example. It's getting harder and harder to actually find bad example. So I think it's possible it'll be alleviated. It's just like it become like a practical, good enough solution, but the problem may not be totally solved. There's a possibility of that. My personal example is like email spam filtering. Just like we still have email, like junk mail, everyone, but it's not as troublesome as 10, 15 years ago. It's not, I mean, the problem is still there, but it's in a controlled way that the level of noise is actually kind of somewhat negligible. Yeah.
Then the follow-up question will be that should we try to solve it 100% or like junk email if they are still there?
Right. I think that fundamentally goes back to like general issues about large language model, like safety, controllability, all those kind of things. You can argue that maybe we handle the head things actually pretty well, so it's not super valuable for a company to invest a lot on that. But I believe that there's always a mission critical things that these kind of things will be important. I use like mostly the general knowledge as the example here, just for like everyone to understand. But it's not hard to imagine that if you're a doctor, you really want to trust this, then in this case, you like for medicine, like 10 milligram is actually very different from 100. So those kind of things actually, even no matter how small it is, if there's some mission critical things, I think these things will still be very important. Yeah. Yeah.
Yeah, I think this, my question kind of relates to the idea of the knowledge boundary.
Mm-hmm.
I'm interested in what approaches do you think about if the context retrieval method kind of fails and doesn't give you the context that you would need to answer the question?
Okay.
Like how the model is outputting, how confident it is that the answer it's giving you is correct. Like I think about a recent use case of mine is I've been working with like an async context manager in Python, which the Claude models don't really seem to know a lot about.
Right.
And the questions I'm asking aren't giving me back the right, context.
Right.
But it will just tell me things, like it knows it's
Right, right.
But how do we encode some of that? Like, here's an answer, but I'm not sure about it.
Yeah. Okay, I think your question may contain two different questions, but so let me just try to answer. One is that if you have some kind of external signal, can the model judge like how reliable the external signal is? Yeah. The second is that whether how does it judge itself? Like, do we have that piece of knowledge or not? And these two are kind of separate problems. We haven't tackled the first one much yet, so all the things I talk about today probably just based on this implicit assumption that there's some ground truth we believe that we don't challenge that, and it's somehow given by the retrieval component. And then because of that, the earlier things I talk about is maybe the, let me see, like the context-aware decoding thing. Yeah, it's also kind of based on that assumption. Let's see. Yeah, it's fine. So, Angie's question you asked is, what if that is wrong, that context is wrong? Yeah, and then, so we cannot ask the model to, on one side, trust the evidence, and the other try to kind of measure whether the thing is trustworthy. I think that problem probably could be discussed separately. And for example, if in traditional search engine, then there should be some kind of scoring function in addition to the rank to actually help us, or some kind of metadata, or those kind of things. And I think engineering-wise, maybe with that signal, you can already tune the model, force the model to say that, okay, now, given that the context is probably not so relevant, then you should actually kind of take a back of searching. I think right now they probably don't have the mechanism to tell the model saying that how trustworthy the external thing is. And so if with that, maybe the problem will be a little bit better. The second one is trickier. There's some methods like, for example, as simple as checking the probability to see like, how confident it is, or trying to predict the model or different output, and then we check the probability. Those kind of things probably give us a signal. But sometimes what we want really is not just a token. We actually want like a statement, the facts, all those kind of things. Yeah. So I think it's still largely open. I don't have a good answer for that. Yeah. Yeah. We're trying some direction, but it's too early to say that those directions are going to work. Okay. All right.
Can I start again?